Hello everybody. Today we are back with another code walkthrough for an basic artificial neural network algorithm. I am Shrutika, having around 13 plus years experience in various domains, technologies, companies, and now I am working as a freelance data science trainer. So let us give a quick start to our session. Here we are assuming that you have at least some theoretical knowledge about how a simple neural network works, and we will not go into too much theoretical depth of the concept. However, when and where the need arises, I will try to explain the concept in brief. Um, so you would be knowing that a basic assumption behind invention of neural networks was that any kind of complex or simple relationships between the dependent and independent variables can be imitated by a neural network if it is configured to use some appropriate combination of layers and nodes. So earlier we had seen that in machine learning we had used different type of algorithms like linear regression and decision trees and KNN and so many things, depending on our intuition on the type of relationships that exist between the dependent and the independent variables. But when it comes to the neural networks, um, um, it can be said that any kind of relationship between the dependent and the neural networks can be imitated if we have an appropriate number of layers and appropriate number of nodes within those layers. Okay. So here we are trying to imitate a linear relationship between housing price and various other parameters using a neural network. So before jumping in the main code, um, just something about the GPU configuration. So you would be knowing that neural networks need very large amount of data to get trained, and in this attempt it needs very high end processors. So instead of CPU, here we are using GPU, that is the graphics processing unit, which have parallel processing capabilities and are up to 100 times faster than CPUs. So their highly parallel structure makes them more efficient than general purpose central processing units for algorithms that process large blocks of data in parallel. So if the similar kind of algorithm, if we try to run using a CPU, it may take lot and lot of time as compared to if we try running on the GPUs. So there are different kinds of GPUs, and as you can see, here we are using NVIDIA. So in the first set of few lines, as you can see in the program, we are trying to connect to NVIDIA SMI GPU and retrieve information about the same. So just if you see here, we are getting this GPU info variable and trying to connect to that GPU. And if it is connected, then we are trying to get some more information about the GPU that is connected. Okay. So first of all, it is giving the name of the GPU, then driver version, CUDA version that is giving. So those are all like a hardware kind of details, which we won't go much into the depth, but you should know how to connect to the GPU. So moving forward, as you can see, as of now, there are no running processes found on the GPU. Then if we go further, you can see from google.colab import drive. So here what we are doing is we are trying to mount the Google Colab drive on our um, actually Google Drive we are trying to mount on the Google Colab. So as you would be knowing that we can keep our data on the Google Drive. So in this way we are trying to connect the Google Drive to the Google Colab, and then we will be able to read the data that is there on the Google Drive. So going further down, so these are the different libraries as we had seen in our earlier algorithms also. These are the basic libraries which are used by mostly all of the machine learning as well as neural network algorithms. So the various libraries like NumPy, Pandas, Matplotlib, and Seaborn. So once again, NumPy used for various array and algebra related operations. Then Pandas we will be using for various data related operations like reading and writing data to a CSV file into a data frame, etc. And then Matplotlib and Seaborn for various data visualizations. So Seaborn is built over Matplotlib library, so it will provide some additional plots like heat map, pair plots, etc. And then, as you can see, NP, PD, etc. These are the aliases that you'll be using in our code for the libraries. And then you can see the line Matplotlib inline. So this line is there to get the plots in line with the code, that is to get the plots right after the code is executed. Then if we go further down, you can see that we have imported the warnings, and then we want to filter the warnings having the tag as ignore, so that we don't get any unnecessary kind of warnings and creating a mess around our code. We want to keep the execution of the code very clean and concise, so that is why we are trying to ignore the unnecessary warnings. Okay, and then if you see here, we are using pd.read underscore csv. So pd was the alias for the pandas library, and we are using that pandas library to read the csv file which is having the data, and that csv file is actually located on the Google Drive. So here, if you can see, earlier we had mounted this Google Drive, and from there we are trying to read the data. So once the data has been read, we are trying to have a glance through some of the initial rows of the data using the data.head command. So here you can see that 5 rows, for the first 5 rows you can see on the screen here. Okay, at the same time, there are some column names like CRIM, ZN, Indus, and all these things, out of which age we know what exactly it is, then text we know, ls stat we can say yes, something that we know about, but apart from that, some other columns are there which are like not very clear. So it is possible that they have been decoded so as to keep um, the confidentiality of the data intact. Okay, but definitely this MEDV, this being the last column, should be the dependent variable or the target variable, and the other columns, as you can see, there are 1 2 3 4 5 6 7 8 9 10 11 12 13, around 13 columns if we have counted correctly. So yes, total 13 columns are there, out of which 12 will be independent columns, and the 13, the last column, will be the dependent column. Okay, so let us move ahead. We will have some more data analysis, data visualization, and then we will start to create the neural network. So then we are running the command data.info. So which is giving us some more information about the data. As you can see, 13 columns are there, out of which all of them are numeric, because either they are float or integer. So all of them are numeric columns. We don't have any categorical column here. And then if we see, there are total 506 entries, means 506 observations or 506 rows are there in the CSV, and out of this, one by one it will start giving us the the non null values for each of the columns. So for CRIM we have around 486 non null values, for ZN also around 486, and then coming down, NOx, RM, these are some columns which don't have any null value, because of which they have the total 506 non-null values. Okay, so moving further, so from data.info also we were getting some information about the number of non-null values. Further down we are firing another command, data.isNull.sum, which will give us the total number of null values for each of the columns. So here you can see, so these are the most some of the most important commands which will be used in each and every algorithm, whether it is an ML algorithm or a neural network algorithm. So these are some commands which should be at your fingertips. So just moving forward, as you can see now, the next is some function that has been defined. The function is null values def null values, and which is taking some input parameter as data. So actually this is a very important function if we are having lot of columns and a lot of rows if we are having. So it this function will come out as very handy. So let us see what exactly this function is doing. If you can see, here we have defined an ls list. Okay, so here we are initializing an empty list, and then we are recursively going through each of the columns of the data. Definitely this data is going to be a data frame, and for the data frame, from for each of the columns we will be recursively going through each of the columns in a loop. And if for that column total number of null values is greater than 0, then we are appending that column as well as the total count of null values to this list. You can see ls.append. Okay. After that, we are checking the length of ls, means whether ls is having any value or not. So if at all we have any null values, then those values will be stored in the ls list, and we will get the length of ls as more than 0, and it will come into this if loop. Okay. And now what we are doing is, for each of the columns we are finding the percentage. So it is some simple algebra we have which we have used to find the percentage. Okay. And now if we call this function for the data frame, we will get something like this. Okay. So the first line says is null values are present in these. It is giving the total number of columns as well as the total number of null values for each of the columns. After that, it is giving the percentage of null values for each of the columns and the data type. Why it is required is, if the percentage is as low as 1% or 2% of null values, okay, then we will try to fill those null values depending on the data type of the column. And sometimes if the null values are as high as 95% or 96%, then it is better to drop that column actually. So depending on some other factors, a lot of times we tend to drop those columns. So that is why this percentage is required. So if you can see, null percentage in CRIM is 3.95 and data type is float. Okay, so what does this mean is, because the null values are less as compared to the total number of non-null values, so instead of dropping the column, there is no point dropping the column. The column can might be significant enough in predicting the dependent value. So we will never be dropping this column, but we will be finding the mean of all the values in this column, and we will fill the null values with those means. So that is why the data type is also required. So if the data type is numeric, then we'll be using the mean to fill the null values. And if it is a categorical, then we will use the mode. Mode means the most frequently used values. Those will be used to fill the null values. Now moving further, so as you can see here, if the for that data, if the null values are more than 0, then we are filling those null values with the mean of all the values in that column. Okay, so that is what we are doing. This is called the null value treatment. And then again, if we try calling the same function for the data frame, we can see the output is no null values. Okay, so finally we have done the null value treatment, means whatever null values were there for each of the columns, we have replaced them with the corresponding mean value for that column. So one step, that is the null value treatment, is done for our data frame. Moving forward, so the next thing, as we discussed earlier, this MEDV column, that is the target column or the dependent variable. Okay, so what we are doing is we are taking that dependent variable, specifically that dependent column, in another data frame, that is the Y. Okay, and then from the data frame, the original data frame, we are dropping this column MEDV, and then we are assigning all the rest of the data frame without the MEDV column to the X variable that we are declaring it now itself. Okay, so if you just see this command data dot drop, means from the data frame we are dropping, what we are dropping, the MEDV column, and then we are giving x is equal to 1, means this we are dropping it from the columns, not the rows. If x is equal to 0, it means that we are trying to drop something from the rows, but in this case x is equal to 1 means the program will try to find this value MEDV in the columns. Okay, and once if it finds it, it will drop that column, and the remaining of the data frame, it will be assigned to X variable, while the data frame with only MEDV column will be assigned to the Y data frame. Okay, now if we try to check the size of the X and Y variable, we are running the command x dot shape and y dot shape, and as you can see, the X variable, that is all that which is having all the independent columns. Okay, it is having the shape of 506 and 13. It means that the total number of rows are 506 and the total number of columns are 13. Okay, while for Y, the independent variable, to the total number of rows is 506, while it has only one column, which is why this has not been exclusively displayed here. Okay, so it is quite obvious that this 506, it is going to be the same, because the total number of rows has to be same for both the X and the Y variables. Now we will move ahead. Okay, so now here we are importing the model selection library from scikit-learn to split, to get a train and test split. Fine, so if you can see, we are calling the function train test split, and we are providing both the X and the Y variables, and we are defining the training size as 0.75. So obviously the test size is going to be 1 minus 0.75, that is 0.25. Okay, so if you can say, all these values will be assigned to the X train, X test, Y train, and Y test variables. Fine, and now again, if we try to find the number of rows and columns for each of these variables, you can see that X train and Y train are having total number of rows as 379. If you just take 75 percentage of 506, you will get something as 379. So that is why 379 total number of rows for the training set, that is the X train and Y train, while the remaining 0.25 percentage of 506, which will come out as 126, that we have taken as the X test and the Y test data frame. Okay. Now the number of columns in the independent variable is 13 here, as you can see in the train set, and it will be exactly similar for the test set also, that is the 13. Okay, and for the Y, that is a dependent variable, it is going to be 1, because of which you will, it has not been explicitly shown here. So if you just see, the total number of rows will be similar for the training set of both X and Y, as well as the test set of X and Y. And the total number of columns will be same for X train and X test, and Y train and Y test. So it is just a cross check for you to check if the things are going fine or not till this point. Okay, so somewhere if you see that X train is having the number of rows is 379, but Y train is having something like 340, it means somewhere you have done some mistake. It has to be 379 in both X train and Y train. Similarly, if you see that the number of columns in X train is 13, but the number of columns in X test, it is somewhere 10 or 11, then again there is some mistake that has been done earlier, and you need to check the program, because it is definitely going to give an error when you run it on the when you take this data to create the model actually. So now moving ahead, next what we are doing is we are importing the mean squared error from the scikit-learn matrix library. So as you know, this mean squared error or the MSE, okay, generally we use this to find the deviation of our predictions from the actual values. At the same time, we are using some simple arithmetic library math to get the SQRT, that the square root function from that. And then again, we are taking the R2 score from the scikit-learn matrix library. So these are the different kind of scores that we'll be using to check the accuracy of our program, that how good our model is working. So the mean squared error, R2 square, these are some of the things which we'll be using on our fitted values to see whether our model is giving the expected results or not. So moving ahead now, next you can see there is a function analyze which we have created, and we are passing three parameters here. One is the model that we have created, and the other are the X data frame and the Y data frame. So now onwards, X data frame means the independent variables and the Y data frame means the dependent variables. Now what exactly it is doing, this function, that we will see after some time when we are going to call this function. But before that, let us see how we are creating the model. So now this point onwards, we are creating the artificial neural network model. So let us see what exactly the things are being done. So here, if you see, okay, we'll be using Keras library to create layers and nodes for the neural network. So if you see, we are importing keras.models, keras.layers, okay, and all these libraries will be used to create the layers and nodes for the neural network. So what exactly Keras is? Keras is a powerful and easy to use free open source Python library for developing and evaluating deep learning models. It wraps the efficient numerical computation libraries, Theano and TensorFlow, and allows you to define and train neural network models in just a few lines of code. So as you will be seeing, some any kind of complex architecture we will be able to make using just a few lines of code using this Keras language. So this is the first is the baseline model that you will be creating. Okay. So what exactly we are doing, let us see. The first thing is we are creating an instance of the sequential model. If you see here, we are calling the sequential to create the sequential model, and sequential is the easiest way to build a model in Keras. It allows you to build a model layer by layer. So that is what we'll be saying, seeing how the model is being created. So we are adding first layer, which is the input layer, okay, with the input dim as 13, which is equal to the number of independent features. If you remember, the number of independent features in our X data frame were 13. So this has to be equal to 13. Okay. And then we are using some kernel initializer as normal, and we are using an activation of ReLU here. If you can see, activation we have defined as ReLU. So what is ReLU activation? Let us see in brief. We will discuss this thing. So ReLU activation, it is one of the most popular non-linear function, and the it stands for rectified linear unit. In a generalized way, the output of the function will be 0 when x is below some threshold and will be equal to x after that threshold. Okay. So in short, when we apply ReLU to a node, it will output the value of linear function directly if it is positive. Otherwise, it will block it. Okay. So actually, let me see if I can show you the architecture diagram. So if you can see here, this is the architecture diagram of the basic artificial neural network. Okay. So these are the network inputs. In our case, there will be 13 inputs that will be going. Okay. And they will be going through this layer, and then the activation that we have used is ReLU. So the output will be, the first will be for all these columns, the weights and the biases will be applied, and whatever is the output, on that output the ReLU function will be applied, and then the output of that, the input layer, will be going to the next layer. So just to give you some small idea, I have shown this neural network, and as you can see, this will be the feed forward, the forward pass, and we will get some output, and then again there will be a back propagation to check the output and adjust the weights and biases accordingly. And this one set of feed forward and the back propagation, it will be called as one epoch, and in this way a number of epochs will be done. So finally we get an optimum value of the weights and biases. So in very short, I have just explained this artificial neural networks, so that you people are able to recollect whatever you have learned in theory session, and we are able to move forward. So I will just open the code once again. Okay, so I'm I hope you people are able to see. So as I have shown in the diagram, so this is the first input layer, which is having the 13 number of inputs. Okay. And then after the ReLU activation is applied, the output will be sent to the another layer. And in this case, because we have just two layers, one is going to be the input layer and the other is going to be the output layer. Okay. So the next layer is also dense layer, and we are having only one value in the next layer, and the kernel initializer is normal here. So these are some settings which we'll be discussing in some of our later videos, that what exactly it means and when and where to apply which setting. So we have created the different layers, and after this, when we are compiling, we start compiling the model. And when we are compiling the model, we are passing the loss that we want to use, that is the mean squared loss error, and the optimizer. The optimizer is NM. So just remember that when we are compiling the model, at that time we will be passing the optimizer and the loss function that we want to use. Otherwise, the number of input nodes, the activation function for each of the layer, all these things will be defined when we are creating the layers one by one. So this is the baseline model that we have created. Now moving forward, now what we are doing here is we are assigning estimator to the Keras regressor. Keras regressor, in turn, it is a library from scikit-learn wrappers. Okay. And in the Keras regressor, we are sending the baseline model. Okay. So the model will be created when this Keras regressor runs. At the same time, we are setting the number of epochs as 100, batch size as 5, and verbose is equal to 0. Okay, so when this Keras regressor is run, the first thing is it will run on a model which has one input layer and one output layer. At the same time, the total number of nodes in the input layer is 13, and the activation is ReLU and the optimizer is Adam, as we have described here in the baseline model. So this model will be created first of all, then it will be run 100 times. As we know that one epoch is equal to one set of one forward and one backward propagation, when this one set is called one epoch. So 100 times it will be going forward and backward in order to adjust the weights and biases, so that we start getting the optimum prediction value. So epochs we have set as 100, and then the batch size is 5. What does this mean is, in each um, what we can say that when this Keras regressor is running, at a time it will be taking 5 number of rows from the data for processing. Okay, so for these five rows they will be sent. So let us say, as we saw that in training there were around somewhere 300 number of rows. Okay, so 300 divided by 5 means around 60. So 60 times you'll be sending the data, and this 60 times will be sending the data for 100 times. In this way you have to understand it. Okay, so in this way the Keras regressor will run to get the optimized weights and the biases. And then the next is the K-fold. K-fold we are using just for the cross validation. So in one of our previous videos, you would have known that we use K-fold to just cross validate the score. In K-fold, what we'll be doing is we will be dividing the data frame into n number of equal data sets. So if you can see here, we want to split the data frame into 5 equal uh, sets, and out of 5 equal sets, One by one, each of the set will become the test, while the remaining four will become the train. And in this way, the different sets of test and train we will be using on the model to check what is the value of the score that we are getting. So in this way, we will be able to cross validate. If the scores are not too much varying from each other, then it means that the model is working in a good way for us. In this way, we can understand that this is one of the requirements, that the cross validation scores, the score should not be varying too much, and if at all it is varying, then we'll take the mean of all the scores. So that is what we are doing here. Now, in the cross validation score, we found that the mean is somewhere minus 32.09. That is what we understand. So the next thing is, if you can see, again we are running the cross validation score, and this time we are, the other parameters are same: estimator, x train, y train, cv equal to k fold. Only the thing that we have changed the scoring, that is this time we want the r2 score. And now if we see, if the value of r2 is changed, we are getting some another values, because definitely now inside algorithm will change to give us the different kind of score. Okay, after seeing these scores, we started fitting the model, okay, or training the model. So estimated dot fit is doing the same thing, and we are passing the x train and the y train data so that the model gets fitted, or the model gets trained in another language. And now here if you see, we are calling the analyze function. This function we had seen earlier, and we had said that I will explain it later when we actually come across this function call. So now we will go back to the function and see exactly what it is doing. But before that, just this analyze function, we are, this is the estimator model and the data set that we are sending to this analyze function. And if we come down, this analyze, it is giving us the RMSE value, which is 4.65 something. R2 score, it is giving at 0.7379. So as you would be knowing that the best R2 score will be near to 1. So we can say that it is not very poor, considering the first time we are creating the layers, and it is just one input and output layer. So it is doing a fair job. Okay, and we can see some plots also. Some error distribution plot is there, actual versus prediction plot, and residual plot is there. So if we go through the plots one by one, we can see that in the error distribution, the x-axis is having error values and the y-axis is having count. Okay, and the peak you can see, it is not exactly as 0, but somewhere towards the right side of 0. The peak, it is around 40. It means that there are around 40 observations for which the error lies somewhere between 4 and 5. If we just try to guess this value, it will be somewhere between 4 and 5. Okay, so it means that the model can be further improved, definitely. Now moving on to the actual versus predictions. On the x-axis, you can see the actuals are there. On the y-axis, you can see the predictions. Okay. So we can see actuals means the actual values of the dependent variable and the predictions that we have got from our model. So somewhere if you can see, if for see just these few initial points, if the actual value is low, the predictions are also low. Okay, and somewhere going here, towards the right top portion. If the actuals are high, the predictions are also high. So it is doing a fair job. But somewhere we can see outliers also, right? That somewhere the values, the actual value is high, but compared to that, the predictions are not that high. So definitely some outliers are there which will call for the improvement of the model, but still we can say that the model is not doing a bad job at all. And now moving on to the residual plots. Okay. So here we can see that the residuals means the difference of the actuals and the predictions. So ideally speaking, the residual should be zero because the prediction should be exactly equal to the actuals. Fine. So if you see around zero, you can say that most of the in this scatter plot, most of the points are um, gathered on the zero axis where the residuals are zero. Okay. On the x-axis, the y values are increasing. Okay. But mostly the residuals are zero, but still you can see there are some points, some outliers where the residuals are more. So more towards both the sides, towards the positive as well as the negative side. So if you can see for 25, the actual value of 25, okay, most of the this thing is dense around zero, but there are some points. Here you can see that the residual is more than 15. The topmost point, if you can see, the residual is more than 15. At the same time, for a similar value, we are getting the residual as minus 10 also. Okay, so the intuition that we can make out of this residual plot is most of the residuals are zero, but still there are some outliers lying on both the sides of the zeroth axis of the residuals. So moving further, okay, so let us see what now we saw. This is the output, the graphs and model RMSE R2 score. These are the outputs of the analyze function. So it is using some basic matplotlib and Seaborn charts to create these plots, and it is using some basic libraries to arrive at the RMSE and the R2 scores also. Now the same function analyze we have used now for the estimator, the same model, but the test data. Okay. And now you can see that for the training data, we were having RMS is 4.6, R2 score is 0.73, while for the training, it has increased. The RMSE score has increased, while the R2 score has also increased. Both of them have increased now. And if you see the error predictions, the plots, okay. So in the train, you can see there are more peaks on the both the sides, okay, as compared to the training. And this residual plot, it will clearly say that if you see here, the the points are more gathered towards the zero value of residual, but here you can see that it is getting scarce. They are not, the points are not that dense where the residuals are zero. So definitely on the test, the results that we are getting are not as good as that are on train, which is very much expected from any kind of model actually. Now, just for the experiment purpose, we are creating some another models also. So here, if you can see, we have created a larger model. So initially, we have just declared a model, a sequential model. The first line is exactly same. We are creating 13 nodes here. Fine. And kernel initializer is normal and activation is relu. After that, actually, we have added one more hidden layer, okay, and which is having 6 nodes. And then finally the another output layer is there, which is not having any activation. Here you can see that both the input layer and the hidden layer is having the activation, but the output layer is not having the activation. And now, as discussed earlier also, when we are compiling, we will be providing the loss function and the optimizer. That is what we are doing. So this is some experimental model that we have created, which we can try running. So the same code we have used here, okay. So the same function we have used here, we have appended some standard scaler to scale the data, and then keras regressor where we are using the larger model. Because this is a larger model, we are using the number of epochs as just half. Earlier we had used 100 number of epochs, now we are using 50 epochs. The batch size is same as 5, and then this time earlier we had done n splits of 5. This time we are trying the n splits of 10 for the cross validation score. So cross validation score, it is just for some experimental purpose, but it won't give any real time significance actually, specifically for this algorithm. And we will have still to get this fit estimated dot fit done, estimated dot fit, or the pipeline dot fit done. So this pipeline, it will start running one by one all the commands which we have already inserted into pipeline. So here you can see we have defined the pipeline with the estimator. So first of all, it will do the standard scaling, and then it will create the model, and it will start training the model. That is what we are doing here. Okay, and once the model has been created, once the model has been trained, we are calling the analyze function on the same model for the training data. And now if you can see, this RMSE have reduced. Earlier it was 5 point something, now it is 3 point something, and the graphs you can see they are much better now. Now the same analyze function we are calling for the test. As you can see, RMSE has increased, okay, and the plots, they are not as good as compared to train, but still you can see a kind of similar trend here. Okay, and the third experiment, it is somewhat a little bit different from the general experiments that we see in the programs. So what it is, a kind of wider model that we are creating. So the same thing, we have created a sequential model, and here instead of 13 nodes, input nodes, we are passing 20 actually. So the number is more than the number of independent variables. So the total number of nodes are 20, but the input dimensions are still 13 here. Apart from that, the activation is ReLU, and then only one output layer we can see. There is no hidden layer anywhere. And we are compiling it, and again we are doing the same thing. We have created the estimator, and in the estimator, keras regressor, for the wider model we are calling, we are using the number of epochs as 100, batch size as 5. So again we started getting some RMSE, and these are the cross validation score, but we will try to see the exact RMSE values from our analyze function after training the model. That is what we are doing it here, pipeline.fit. So if you see the RMSE, so these are the different values, and we can, as we can see, the RMSE slowly somewhere it is reducing. Then as obvious, the same thing, if we run on the test, it is increasing. So in this way we are doing different combinations and permutations of the number of layers and the nodes to get some optimum value of the architecture for to get the best predictions. So that is what we are doing in the program. So hope you were able to get some idea on exactly this new how this neural network we have created, and you were able to map these things with the theoretical concept also. So maybe you people can also try creating these kind of models and running it on your own data and see how the predictions are working for you. Hope all of you enjoyed and learned something from this session. So thank you everybody.